Well, hello, and welcome back to another episode of Quantitative Bites. It's great to see you all. I hope you're doing well. Apologies for not having posted for a while. Things have been a little bit crazy around here, and probably I'm not alone in that regard. But yes, I'm hoping to try to get back to posting on at least something approximating my regular schedule fairly soon. Not making any promises, but doing my best. And yes, hopefully we can get back to weekly videos in the not too distant future. Anyway, this video today, I just wanted to make a quick video really just to wrap up everything that we've been doing with the simple spectrum analyzer app. So over the last 3 videos, I think it is, I've been putting together or documenting my process of putting together a very simple app using C++ and the SDL2 library to create very simple, very basic spectrum analyzer style, frequency spectrum type displays of simple signals from wave files. So we've covered, in the last episode, we covered reading a wave file. I'll put a link up here for that, or possibly this side. I always get confused somewhere. But yes, so in the last episode we covered that, reading wave files, and the previous episodes before we looked at putting together the basic structure of a very simple app that would allow us to do this. Now what we've created is incredibly simple. It's based on the discrete Fourier transform technique that we talked about in that previous episode. Again, a link somewhere up here to that if you want to go and have a look at that. So it doesn't run in real time or anything like that, but that's not really what we've been aiming for. It's really just intended to be a very basic demonstration of how these techniques work and how to go about using these kind of techniques to create this kind of application. So as such, this is going to be the final episode in this series on the spectrum analyzer. It's not really complete in any way in its current form, but it is functional, and what I'm hoping is that it would serve at least as a basis for anyone that's interested out there to go ahead and create their own version of this code and then take it from here to wherever they want to go with it, rather than me pursuing it to some kind of final app in these videos. I always intend these videos to be more inspirational than anything else, more about inspiring people out there to my viewers and people out there to go to create your own code, to create your own things rather than simply copying mine. And so I'm not going to document this any further. I'm going to continue working on it myself privately for my own purposes, but I think in terms of making these videos, I feel we've gone far enough. We've gone as far as we need to for that. So these videos really are intended to be educational and inspirational, really. Nothing more than that. I'm not sort of showing the process of going through to creating a complete product or anything like that. So yes, so on that basis, this will be, as I say, the final episode in this series. Now, there isn't actually a lot that I've done to the code since the previous episode, except to get it ready to actually produce an example animation. So you can see here right now, this is an example. This was produced using the code that we've been talking about in this series. And as you can see, the spectrogram display here follows my voice as I'm speaking. Okay, now it's a very short example because the way this software works is it's quite slow. So what it does is it pre-generates, you extract the audio you want into a wave file, and then you run that wave file through the spectrum analyzer code, and it generates a series of images for the animation, and then I've just imported those into the video in order to show that example. So in a moment we're going to go to the computer and have a look at exactly what the code is that we needed to do that. But before I do that, as I always do, I just wanted to say that if you like this video, please do remember to hit that like button. And if you haven't done so already, please consider subscribing to my channel. As I say, I do try to post videos roughly once a week. Just recently, I haven't been able to achieve that because there's been a lot going on and various things, but I'm hoping to get back to that. So if you subscribe, you don't need to worry about missing any future content. Great, thank you very much. So anyway, without much further ado, I suggest let's go to the computer and let's have a look at the code that I've added since the previous episode that allows the creation of very simple animations such as the ones we've just seen. Okay, so here at the computer, this is the code that we've all seen before. I'm really just going to go over the code that's changed since the previous episode, which, as I said, actually isn't that much to make this into something that could be described as basic but fully operational. So the first thing we have, looking in specplot.h, so this is in the qb speclib folder. Just as a reminder, actually, let's just have a look. So what we've got for our code, we have here, we have the various files. So we have capp.cpp and capp.h, that's the class for the actual main app. We're going to look at that as well in a moment. Then we have main.cpp, which is our main file, and then we have the qblib2d folder there, which is our 2D primitives library, and we have the qbspeclib folder there, which contains, if we go into that, it contains the file specific to doing our plotting our spectrogram. So we have qbdsp.cpp and .h, and that contains the discrete Fourier transform code. And then we have qbwavereader.cpp and .h, which is obviously the class we wrote in the previous episode for reading wave files. And then we have specplot.cpp and specplot.h, which are responsible for actually producing the spectrogram display. And that's what we're looking at the moment. So this is the header file, specplot.h, and the only things here that have changed since the previous episode is that I've added two new methods or functions, which are set Dft length and set bar height scale. So set Dft length can be used to specify how long you want the DFT to be in terms of how many bins. And the reason we have that now is that I want it to be possible to set the Dft length independently of the number of bins that we're using in the display. Now I'll explain that in more detail in a moment. And also set bar height scale, so this is going to be used to simply specify a scaling factor for the height of the bars. We don't necessarily want the bars to fill the whole screen vertically, so we can specify a scale factor here between 0 and 1 that will control that. So obviously a value of 1 is going to give bars that fill the whole screen vertically, value of a half, they would fill half the screen, a quarter of the screen, and so on. And of course that accepts a float as input, and the Dft length accepts an integer as input. And then the only thing that we've done as well is to add an m bar height scale variable here in the private section there, which is simply a floating point. Okay, so if we go to the CPP file for that, specplot.cpp, there's a few more things that have changed here. So first of all, we've added our function for set Dft length, so that's this code here. A very simple method to do that. It accepts length as an integer. It simply stores that there. And the one thing that we have to do is we have to recalculate the window that we're going to use. If you remember, we used a Hann window from the function that we defined in qbdsp. And so that was pre-calculated to be the same length as the number of DFT bins. And previously, because the number of DFT bins was fixed at the point that we created an instance of the specplot class, all we had to do was pre-calculate the window function when the class was created, and then that would be fine. But now we're allowing the user to modify the number of DFT bins, and theoretically, at any time. We have to pre-calculate the signal window. So we use the .clear method because signal window is based on the vector class from the standard library, and then we simply call the qbdsp : window Hann function and specify the window length, and that will give us our new window. And that's that. That's pretty easy. And then we have a function to set the bar height scale. That's really, really simple. Just accepts scale as a floating point input and simply stores that into the m bar height scale variable. It doesn't need to do anything else. And that's everything for that. Now, one other thing that I have modified here is in the set data method. So this is the function that actually does all the clever stuff. I'm not going to go over it now because we talked about it quite extensively in the previous video where we developed this code. The one thing I do just want to mention here is max value. Now, what we did before is we calculated the maximum value for every chunk of data. And that was fine for all of the test cases that we ran so far because the power or the level or the amplitude of the input signal was constant over time. Now the problem with using this method, if you have a signal whose amplitude varies considerably over time, or perhaps a signal that contains quiet moments where there's no actual signal, is that this is essentially going to really just show the power spectrum of the noise floor, because it's going to effectively, it's normalizing for every chunk. Now the proper way to do this would be to run over the whole signal first as like a pre-passing step, and find out what the maximum value of this is for the whole signal. And then when you go through doing this process of extracting the chunks to actually make the display, we would normalize by that fixed value. And then so everything would then be scaled according to what was the maximum value in the signal. What I have done in this case, though, is simply specify. So I've hard-coded a maximum value of 50,000. This is really not a good way of doing things, but it's okay for now and really just helps to illustrate the point, and this gives us something that works now. Moving forward, this is something that I'm going to look at changing myself, and I think that could be done in a much better way, as I've just described, but we'll go with that for now. And then I put this line of code in here simply for debug purposes. So that's how I got to the value of 50,000. I printed out the max values as it went through and had a look at the range and picked 50,000 as a reasonable value. Okay, one last thing also there, because of that we need to insert a little bit of extra code here. So we extract temp value, which is 10 times log to the base 10 of the absolute value of the discrete Fourier transform at the particular sample. Okay, and we then store that. We've talked about this code before. What I've added here is this if-else block here. So if temp value is less than minus 30, we're in dBs now, okay, so as it's described in the comment there, then we push back 0.01. If temp value is less than or equal to 0, then we use the temp value as it is. If, on the other hand, it's greater than 0, then we know that we've exceeded our maximum value. So that would mean we're taking the log of a value that's now greater than 1. So we simply push back a value of 1, bearing in mind that for the maximum value here, this would be temp value of 0 plus 30, which is 30 divided by 30, which gives 1. So we know our maximum value is 1. Okay, that should be quite straightforward. Okay, and finally, in order to accommodate the situation where we have a different number of DFT bins compared to the bars, I've also modified this code here. So one thing that I've done here now is calculate a bar step, which is the size of the power spectrum divided by the number of bins that we want to display. So the power spectrum contains half the number of bins in the DFT. So if we set the Dft length to 1024, then the power spectrum is going to contain 512 samples. So whatever that is, we take that number of samples and we divide it by m_num bins, which is the number of bars that we want to display. So what we're going to do is step through the power spectrum with a step size calculated from this, and then all we do is we loop through the power spectrum. So we're looping I as our loop variable for I as less than power spectrum.size, I plus equals bar step. So we go through in steps of bar step that we calculated there, and that gives us bar height, which we then store bar height of count. Count starts at 0 is equal to that value from that sample from the power spectrum, multiplied by m bar height scale, which is the new variable we introduced to allow the bars to be scaled. And then we simply increment count, and we do that until we reach the end of the power spectrum. And then, as before, we simply call update bars, and that will produce the display. That is actually everything that I've modified in the specplot class. As you can see, it's not very much. And that is enough, though, to allow us to do something a little bit useful, or not useful perhaps, but at least interesting. Now the CApp class, if we look back at the code, here we are, and go back to the main folder, capp.cpp and capp.h. As we said before, this is the main class for the application. Now I've added some stuff here to do with writing out images. So what this code does now, when we run it, it will produce a sequence of bitmap images for our animation. And then the idea is you can take those images and import them into your whatever video editing software you use, or whatever tool you want to use to do that, and you can then create an animation from those. In order to do that, we need some various stuff for writing images. Now there's more details on all of this available in the relevant SDL2 documentation pages. I will put links to that in the description below. Really good resource, really recommend you go and look these things up. So the first thing we need is an SDL surface, which we'll simply call m_image surface, or pointer to that, pointer to an SDL surface. we need a uint32 number called mchroma key. Now we're going to use that to do transparency, and we need an integer to store our frame count. So the point of frame count is simply to increment frame count with each new frame so that we know where we are. And now if we look in capp.cpp, we can see various things that have changed here. So now we have this code here now. Initialize the stuff we need for writing images. Okay, so we can see that goes in just after so we're in the initialize method, and just after we call SDL get render output size, we now have this new code. So we instantiate our image surface using SDL create RGB surface, and we're passing it these parameters. Now for now I've just hard coded the masks for red, green, blue and alpha. These will depend on your system. If I'm running Linux and if you're running Windows, I'm conscious it uses, I think, a different endian encoding, so these will be different. This is all described in the SDL2 documentation, so that's really the best place to look for more details about that. We need to configure our chroma key. So chroma key, m_chroma key was a uint32 variable, and we use the SDL map RGB function to generate a number based on the format of our image surface. So we call mImageSurface format to get that, and the color we want to use is 000 or black. So that's the RG and B values of the color that we want to create to use as transparent. So every pixel that is black in the image will be rendered as being fully transparent. Okay, and we initialize the frame count to 0, which makes perfect sense. Okay, and now there's some minor differences here. So one thing that I've done, I've set this up with a Dft length of 512, and I've set the bar height scale to 0.25 so that the maximum height of the bars represents just 1/4 of the vertical size of the screen, which I think gives quite a good display. Now in execute here, we have some slightly different code here where we configure the wave reader object. So we're in the execute function now, and we configure our m_wave reader object. This was wave reader class was described in the previous episode, so go and check that out if you haven't seen it already. And what we're doing here, this allows us to specify effectively what the frame rate is going to be. So we're wanting to make an animation. Now I want that animation to fit into the video I'm making here, simply for this example. Now I render my videos at 29.97 frames per second, and that works out at 0.0333 seconds per frame. Now our audio file, the WAV file, consists of 44.1 thousand samples per second. So if we take 0.0333 seconds and multiply that by 44.1 thousand samples per second, that tells us that we need 1,472 samples per frame of our animation. So in order to achieve that, we just have to set the chunk size of mWaveReader to 1,472 and the chunk overlap to 0. So there'll be no overlap. Each chunk is 1,472 samples, and that should correspond exactly to 0, or close enough to 0.0333 seconds, which will then mean that we get an animation that, when played at 29.97 frames per second, should match accurately enough with any other video or anything going on. At least that's the theory. And while I can confirm it does appear to work. Okay, yes, the one other thing I should mention here, I forgot to mention, just that when we configure the new specplot object or instance of the specplot class, we're specifying 128 frequency bins. We're specifying a Dft length of 512, and we have a chunk size of 1,472. So this is one of the things, you note all of these numbers can now be different. So we're taking 1,472 samples from our signal, we're then calculating a Dft of length 512 samples, and then we're rendering that into 128 bars. Okay, a little bit confusing, but I think it should hopefully all make sense. And that is just about everything. So the only other bit of code that we've added is actually to do with outputting the images. And where are we? This bit here, SDL free surface. So just when we finished, so in where are we? Yeah, in the execute function, when we drop out of the main loop, meaning that the code is going to execute, we have to use the SDL_free surface function in order to free the surface pointed to by our m_image surface variable. That's fine. And now in tick, what we have now, we have this chunk of code here which is new, and this outputs the current frame as an image. Now this is really slow doing this because we're using the SDL_render read pixels function, which the SDL2 documentation describes as being very slow, but it is the best way I know of getting the final image from our window and being able to write it out as a bitmap. Because this is already very slow, I haven't worried about execution time in terms of fast Fourier transforms or anything like that, because I think this is pretty slow anyway. The way this works is all well described in the SDL2 documentation, so I really suggest you go and look at that. But to set this up to actually write the images, the first thing we need to do is automatically generate our file name. So we simply specify a small buffer of type char, 5 bytes long, and then we print into that current frame count variable using sprintf, and then we specify a instance of the string class from the standard library called file name. We specify the root path to that, which for me in this example that I'm doing is /animation/frame, and then it's going to be frame 0001, 0002, 003, and so on. And then we simply do filename.append the buff, which will give the contents of that array, and filename.append.bitmap, so that we add the file extension. So file name is now an instance of the string class from the standard library that contains the full path and file name that we need to write to. We use SDL render read pixels, as I've just described, to take the contents from mRenderer and write that into image surface. As I said, look at the SDL2 documentation for more description about that, link in the description below. And we set the chroma key using SDL set color key. We specified the chroma key variable before, we've talked about that, onto image surface, and then we simply use SDL_save bitmap, which will write the image surface contents of image surface to file name.c_str. Okay, and then we increment the frame counter, and then of course every time we come through tick, frame counter's incremented, so it will generate the next frame, and that's it. The rest of the code is exactly as we've described before. So all that really leaves me to do is let's just go back to my terminal window. Now, if we look, I have already gone ahead and built this code. I haven't made any changes, so I'm not going to worry about compiling it. And I have a variable here, audio extraction1.wav, a file, sorry, audio extraction1.wav, which is the 10-second audio clip that I extracted from my video for the purposes of making the example that you've just seen. And to run the code, we simply do /main after building it, of course, and pass to it as input audio extraction1.wav. And I need to just bring this window over so you can see, and what that's doing is now running, it's generating the spectrogram for every 1472 samples of the WAV file, and it's saving those frames as bitmap images as it goes along. It runs very slowly, especially when I'm running my screen capture software at the same time, but this is definitely not intended to be real time. If you wanted to do real time, it's probably possible. I mean, if you disregard the business of saving the images out to disk as you go, and you would have to replace the discrete Fourier transform code I've used with an implementation of the fast Fourier transform. Now, I've deliberately avoided talking about fast Fourier transforms because it's a very standard algorithm, and if you Google for it, you can find example code to implement the fast Fourier transform in any language you like, obviously including C++, and I just think it's really well described, and I felt there was no real way I could talk about that without really just repeating what someone else has said somewhere already, which I didn't think was really very interesting. So it's not too difficult to take a piece of code to implement the FFT from the web somewhere or from GitHub or wherever, and then you just need to create some code to convert the data to the right format for that particular function or library, whatever it is, and then to convert it back if you were to implement that. Or, since I really just hope to inspire people with these videos, and rather than expecting you to copy my code line for line, simply fit your code around whatever FFT library you've decided to use. Anyway, this will run through and it will generate an image for every frame. You don't need to let that finish. And at the moment, what that does, if I go into my animation folder, we can simply see that creates a whole bunch of files. They're simply called frame. These, if I scroll up to the top, obviously, there we go, start at frame 000, .bitmap frame 001, 002, and so on, and each one of those represents a single frame of the animation. And then if you want to do anything with that, you just use whatever your favorite video editing software is to import that as an image sequence. There are plenty of tools available that you can use to do that, and you can then use that to create an animation. So there we go. That's really everything I wanted to talk about today. We've seen the code that I've added. It wasn't much of a change really since the last episode, but we've seen that we can create something that's very simple and creates very simple animated spectrum analyzer displays. So there's all sorts of things you could go on to do with this yourself. You could go on to add code to make the bars change color, to change the configuration of the bars, all sorts of things, or to adapt it to work to whatever your own interests are. But as I said at the beginning, I really hope this video and the other videos in this series, and indeed all the videos on my channel, if you've watched any more of them, I hope they've been inspirational to you, and I hope you feel inspired to, get to the keyboard and bash out some code of your own to create your own things. That's really very much my intention. Anyway, so I'm going to leave it there. In the next video, we're going to start something new, something completely different to things that we've been looking at so far. So I very much hope that will be of interest to you as well. And as I said at the beginning, if you haven't subscribed already, please consider doing so. Then you won't have to worry about missing that content when it comes out. And yes, otherwise, that just leaves me to say that I really hope you've enjoyed this video. It's been a great deal of pleasure making it. And yeah, thank you very much for watching. I really look forward to seeing you in the next video. Bye.